Yep, looks good.
All
I'll give it a
right.
1 minute.
Thank you.
Perfect.
So good morning or good evening, wherever you are. It's morning here. The sun just came up. I am Emily, and I'm going to talk to you today about convection in common envelope outcomes. I'm at the Rochester Institute of Technology in New York, and I'm working with Dr. Jason Nordhaus, and I'm in my final year. So a lot of this that you're going to hear is a lot of my thesis work. Okay, so we've seen this slide a bunch of times already today, but just so that we're all on the same page about the terminology that I use, here's common envelope evolution briefly. So we have our expanding primary as it leaves the main sequence, it expands, it engulfs the companion, and starts this phase of inspiral. And as the companion inspirals, it's ejecting energy and angular momentum into the system. And that energy contributes to unbinding the outer layers and that common envelope of the primary star. So either the envelope is ejected at the end of this, or the companion shreds within the envelope, which we heard Jason talk about a couple days ago, how a companion that shreds within the envelope can also affect its final evolution. So I'm here to talk about convection and why convection. So the reason we're motivated by convection is that we see low ejection efficiencies in common envelope studies pretty across the board. And there's a lot of questions about how these ejection efficiencies get so low. Also, many of these studies show no need for additional energy sources. Someone earlier today was even talking about that there's no need for additional energy sources. And we talk about convection and radiation, which are ubiquitous in these giant stars. They're everywhere. And it's a very natural avenue for moving energy in, through, and out of stars. So if we have convection and radiation included now in this analytic study, we can see this very natural, we've called it a conveyor belt, moving the energy from deep into the star, out of the star, which is going to lower the ejection efficiency in theory. So here is how we went through it. So first, what I'm showing here is a MESA model of an interior, a stellar interior, the radius of the star, 4 solar mass star on the x-axis, and different timescales on the y-axis. In blue is the convective transport timescale, which is the amount of time it takes for a convective eddy, convective bubble, to move from some radius in the star out to the surface of the star. And then in the dashed lines, we have the inspiral timescales, or the time it takes for, in this case, a main sequence, a low mass main sequence star, to move from the surface of the star down to some radius. I've shaded here the convective region in yellow, and this is just the place where the convective timescale is short. And here in pink is a secondary convective region that we don't consider because it is not making contact with the surface. In our papers, we talk about the surface contact convective region, specifically because the convection that touches the surface, we say, can radiate the energy away after moving that energy through the convective region out to the surface. So the idea here is that anywhere that the convective transport timescale is dominant, so anywhere that it is less than the inspiral timescale, the energy that is deposited by the orbital decay of the companion can be carried by the convection to the surface, to an optically thin surface, where then the energy is radiated away. So just comparing the timescales, I just have this graphically for you first. So anywhere that is above, higher than the blue convective transport time, we say convection is dominant. And in these regions, convection moves the energy from the inspiraling companion out of the system. It cannot contribute to unbinding the envelope because it has been radiated away from the system. And then anywhere that the inspiral is dominant, which is down here, we see that the convection cannot move the energy out of the system, and instead the energy goes into the envelope where it can contribute to unbinding the envelope. So just the idea is that where convection is dominant, the eddies can carry the released energy from the companion's decay to an optically thin surface, where it's then radiated away, not contributing to ejecting. And the opposite is true in the other regions. So when we see this, when we do this, we see that the energy comparison between the binding energy of the primary, which is shown in blue here, and the decaying orbital energy, which is shown in these dashed lines. And when we consider convection, these take on a bit of a different shape. So first of all, the way that we define things ejecting the envelope is that anywhere where the orbital energy exceeds the binding energy, we say, yes, the envelope has been ejected. And anywhere that the orbital energy does not exceed the binding energy, we say, no, the envelope cannot be ejected. So anywhere above this blue line, ejects envelope, anywhere below, shreds within envelope. And these X's mark the tidal shredding radii. So if the X happens before the intersection, then this thing is shredding within the envelope. And this is more about what Jason was talking about a couple days ago about what happens when there's a shredded companion within an envelope. So I'm going to focus more on the top here about when things eject. But first I want to show you this cute little cartoon that I spent a lot of time, way too much time making, that talks a little bit more about the idea behind the convective model. So this is a top-down view of a primary star with its maroon convective region, its yellow-orange radiative region, and then the core on the inside, and then here we have a companion. So the first thing that happens is companion inspirals all the way through the star. As it's inspiraling, it goes through a region where it's first in the convective region, and then it moves at some point into the radiative zone. While it's in the convective region, its orbit is decaying, it's releasing energy, and the energy gets picked up by a convective eddy. And that convective eddy then carries the energy that's been deposited out of the star. Goodbye. And so now this thing is still moving through the envelope, it's still inspiraling, but that energy that it's depositing in the convective regions does not contribute to anything. It's still moving in, moves into the radiative zone, it injects energy, and that energy does not get carried away. Instead, it gets pushed into the envelope here. And when it goes into the envelope, it's usually sufficient to eject the envelope. And what that leaves is a companion around your white dwarf core at the radius where the envelope is ejected. So when we can compare these energies, we can find the final separations based on that model I just showed. So this area from the surface down to, let's just look at this dashed purple line. This is the convective region where the energy cannot contribute to unbinding the envelope. And then all of a sudden, when the companion crosses into the radiative region, we can see that the companion now all of a sudden has sufficient energy to unbind the envelope. And this happens at different regions depending on the time scale dominance. So anywhere where these lines intersect, we say this is the final orbital radius, the orbital separation of these systems. So the interesting thing that we see here is that because convection is radiating away a bunch of this energy, convection and radiation together allow the companion to travel deeper into the envelope of the star before the envelope is ejected. And what we see now here with these final separations is that these match a lot of the observations of M-dwarf, white dwarf systems, where you have things that are sub-day periods or things that are a few solar radii wide. So the next thing that we did is we compared that study to a double degenerate study. So instead of using a main sequence companion or an M-dwarf companion, which is what's here, we now are using a white dwarf companion. And so just a note, we're using MESA for all these things. And in order to match these white dwarf masses with MESA, we had to change the mass loss prescriptions, which I know are highly uncertain. So just a note that MESA mass loss prescriptions are very tunable, and to match an initial final mass relationship did in fact have to be tuned quite tightly. Okay, so this is observations of double white dwarf systems with the white dwarf are candidates with white dwarf masses on the x-axis and their separation on the y-axis. And I ran my same code that I just described for you, where the convection, same convective timescale arguments. And I said, if I use a white dwarf companion, what sort of final separations do I get? And so that's overlaid here. And there's a lot of these points in these pink and blue and purple. And this is the final separations and the final masses of the common envelope evolution using a white dwarf companion. There's a couple interesting features on here. We do not use an initial mass function, an IMF. So you see that we match a lot of these observations of these double white dwarf systems, but we also have an excess of these lowest separation systems, which we think or hope could be cleared up with an IMF, and that's work that's ongoing. And we also have this clump that we see here in these lowest mass white dwarfs. So you see this clump also in the observations. That's because there are people looking for these extremely low mass white dwarfs, which are called elms. So there's a lot of elms here, and we see them also with our observations, or sorry, with our models. And interestingly, and this sort of goes along with something else we heard today, but interestingly, this is a result of common envelope happening on the red giant branch, where the white dwarf mass is, the core mass is really low and gets interrupted very early on in its development.
1 minute.
Thank you. So we have these things that are matching the observations because the convection allows the companion to travel deeper into the star. And so in context of planetary nebulae, this is my last slide, and here are my conclusions. So we have convection as a likely key factor in forming these things because it is so ubiquitous in these giant stars. And also we're seeing that it's matching observations of the single degenerate and double degenerate binary systems. And convection is lowering the ejection efficiency, this alpha, very naturally with no extra energy sources and in a way that makes a lot of sense with these highly convective giant stars. And something else really important that we're finding from the study is that alpha, this efficiency, is a function of the internal structure of the primary and maybe should be treated as such instead of a constant number or constant low value. So that's it for me. Thank you so much.
Thank you. Questions? I have a starting question while people get theirs ready. At the beginning of the in spiral, when you're going through that convective zone, a lot of the injection of energy is not thermal, it is kinetic. So you're literally flinging material, you're scooping it up and pushing it aside into, that's your typical mechanism. So that ejection, so that conversion of orbital energy into ejected material is not affected by convection as much. Isn't that the case?
Probably. So the other thing that we talk about with convection that I didn't have time to talk about today was sort of the mixing that goes on. That's not just, that's turbulent. And so it's moving material around as well. So I think with what you're talking about and sort of that turbulence in combination could be an interesting argument and study, but that's not something that we've looked at yet.
Thank you. Miguel?
Yes, I have I don't know if the one question or two, but so I've been thinking about the whole alpha thing for a while, and I agree with you that maybe have it like a function instead of having a constant number will be more helpful, more insightful, especially when you have because you have these certain events of unbinding of the material as the companion goes inside, right? But then you have the question that, okay, so maybe it should be like some kind of derivative, right? Like derivative of the orbital energy over the liberates of the orbital energy over the bounding energy that you are putting in the gas. But it's a little bit noisy. That's well, in the trials I have tried to make, it's a little bit noisy, especially because I work with SPH particles, so it's a little bit discretized. So how do you think we can just approach this situation?
That's an excellent question. So the alpha that we have, that's a function of the structure of our primary, is just a function of energy arguments. So, and it's not a function of time. So these are all things that definitely can be advanced. So excellent question. We should talk more maybe on Slack.
All right. Thanks.
Any more? Oh, no?
Yes, to add to Ursula's comment, yeah, there are dynamical effects which convection can take less. I mean, will not affect much. But on the other hand, you can argue that this dynamical effect may increase even the efficiency of the convection if these dynamical effects increases the turbulence motion in the envelope. So yes, I think the convection can carry some of the orbital energy out. I think it can carry most of the recombination energy out when there is a convection, strong convection. So yes, this work is very important, and yeah, Knight's PhD project. Another effect which convection will not take care of is the angular momentum, of course. So then I think the angular momentum and the dynamical effect that Ursula mentioned together must cause envelope expansion, but less efficient than we would expect. But again, with envelope expansion and more vigorous convection motion, because it should carry the energy, we might expect more dust formation of the expansion, more luminosity, which will have some radiation pressure on dust. So it's not that we don't see anything. There will be some enhanced mass loss rate, but not as we expect in a regular common envelope or if we add recombination energy.
Thank you, Noam. May I invite everybody to contribute with questions that may not be directly related to Emily's talk, but they are related to the session in general. You can also have not questions, but wishes and desires of things to be worked out, measured, or calculated by others. It's always nice to have wish lists for other people to do work and give you those answers. And we'll have a bit of discussion, and then we'll have our break. Raghavendra.
So I would just